Hello, everyone. Today, I'm going to present our paper, Efficient Execution of Deep Neural Network on Mobile Devices with NPU. Deep neural networks, DNN, have been successfully applied to many problems, and mobile applications have been developed based on these DNN models. However, running the DNN models on mobile devices suffer from high computational overhead, which means long processing time and high energy consumption issues. To address these issues, many mobile applications choose to offload the data to the server and let the server to run the DNN models. However, this solution may not be the best one, since the network condition may be very poor and some users may not want to share their data with other servers due to the privacy issues. Recently, many smartphone manufacturers developed a dedicated AI chip called Neural Processing Unit, NPU, to run the DNN models on mobile devices. The processing time can be reduced significantly on NPU. However, the NPU has some limitations. Compared to the CPU, which can run the DNN model using 32-bit floating point numbers, NPU can only support 16-bit floating point number operations and storage. To have a better understanding of NPU's characteristic, we conduct some experiments. We use 3 different DNN models and run it on the Huawei Mate 10 Pro on its CPU and NPU, and compare their processing time and accuracy. As shown in the left figure, the NPU can reduce the processing time by 95%. However, when it comes to the accuracy, as shown in the right figure, we can see that the accuracy is different for different DNN models. For example, running VGG on NPU can achieve the same accuracy, almost the same accuracy as running on CPU. However, 30% of the accuracy loss can be observed in the YOLO and the VocalNet model. To address this accuracy loss problem, we propose to use modal partition technique, which means that we run some layers on the CPU to maintain the accuracy while running other layers on the NPU to reduce the processing time. And processing time reduction and accuracy loss are the 2 important factors in modal partition. And therefore, we first studied the layer processing time and the accuracy loss in the YOLO model. As shown in the figure, the P2 layer means that we only run this layer on NPU while all the other layers on CPU. And it gives us 6% processing time reduction and 4% accuracy loss. Ideally, to perform modal partition, we should move the layers like C6, which has long processing time reduction and low accuracy loss from CPU to NPU to save the processing time. And we should run the layers like C17 on CPU since it has low processing time reduction and high accuracy loss. Unfortunately, many layers like C23 does not belong to these 2 extreme cases. And it is very difficult to determine where to run the layers. And especially when we consider the overlapping effects of running multiple layers, the problem becomes more complex. Moreover, a DNN model usually consists of dozens or even hundreds of layers, and there are many possible layer combinations in it. And it is also impractical to try all the layer combinations and find the best one. To address this problem, we studied 2 different problems in modal partition. The first one is called the max accuracy problem, where it means that the processing time is more important for some applications. For example, a flying drone needs to detect and avoid the trees and buildings in real time. In these cases, we should maximize the accuracy under strict time constraint. Our max accuracy algorithm is a heuristic-based a solution to the max accuracy problem. Its basic idea is to move the layers with higher accuracy loss from NPU to CPU, since it is the most effective way to improve the accuracy. More specifically, initially, all the layers are run on NPU. Then we sort the layers in the model in the descending order based on their accuracy loss. And starting from the first layer, we move the layers from NPU to CPU until the processing time constraint is no longer satisfied. Now let's take a look at some other mobile applications, such as using face recognition algorithm to unlock your smartphone or making payments. For such applications, accuracy is more important, and we should minimize the processing time while guarantee that the accuracy is still above a certain threshold. To address this problem, we propose a heuristic-based mean time algorithm. The basic idea is to move the layers with longer processing time from CPU to NPU, since it has the most effective way to reduce the processing time. Our algorithm works as follows. Initially, all the layers are run on the CPU. Then we sort the layers in the descending order based on their processing time. Starting from the first layer, we move the layer from CPU to NPU until the accuracy requirement is no longer satisfied. Although the max accuracy and mean time algorithm can significantly improve the performance compared to running all the layers only on CPU or NPU. However, they have some limitations. For example, they only try a small number of layer combinations based on heuristic. And some factors like data transmission time is not considered in the problems. And to address these limitations, we propose a machine learning-based model partition algorithm called MLMP. The overview of MLMP is shown in the figure. In max accuracy and mean time algorithm, since they only try a small number of layer combinations, we measure the accuracy loss and processing time on the smartphone directly. However, MLMP wants to try more layer combinations, and it is impractical to measure many layer combinations processing time or accuracy loss on smartphone. Therefore, we first propose efficient method to estimate the accuracy loss and data processing time for layer combination in the model profile module in MLMP. Then based on these models, MLMP runs efficient search algorithm in its model partition module to search for the best layer combination to solve the max accuracy and mean time problem. Now let's talk about the accuracy loss estimation. We leverage machine learning techniques to estimate the accuracy loss. To train the models, we first extract the feature vectors. The features include the layer features, which indicates where the layer is running and how many layers is run on NPU and what is their accuracy loss. It also extract memory features, such as how much memory space is occupied by the parameters and the data. We also include operation features, which indicates how many addition and multiplication is performed on NPU. With these features, we train 3 different machine learning models, and we use some commonly used metrics such as mean absolute error or coefficient of determination to measure the model's performance. And based on this performance, we select the best one to estimate the accuracy loss in our MLMP algorithm. To model the data processing time, MLMP considers the data transmission time. This is because the NPU has its own memory space, and the data must be first moved to NPU before running the DM models on NPU. The data transmission time cannot be ignored since the intermediate data results of the DM model may be very large, and it takes a lot of time to transmit them. The basic idea of computing the data transmission time and the layer processing time is shown in the figure. We leverage the difference between running the whole module and running the partition module. We leverage such difference to compute the data transmission time and further use the data transmission time to compute the layer processing time. With the module profile module, MLMP propose a search algorithm in the model partition module to search for the best layers. Actually, the algorithm consists of multiple rounds. It starts from the layer combinations, where all the layers are run on the NPU. In each round, it explores more layer combinations by moving the layers from NPU to CPU. It maintains a list to keep track of the layer combinations, which maximizes the accuracy within the time constraint. Due to the time limitations, I didn't cover all the details in the algorithm. If you are interested, you can read our paper for more information. And that's for the max accuracy problem. To solve the mean time problem, we use the similar search algorithm. The only key difference is that the accuracy requirement is considered in the algorithm instead of the time constraint. Now let's talk about the evaluation part. In the experiment, we test two different DNN models, VocalNet and YOLO. And we conduct experiments on Huawei Mate 10 Pro. For the layers run on the CPU, we use the Cafe Android library. And for the layers run on NPU, we use the NPU SDK provided by Huawei company. Now let's first take a look at the comparison between different algorithms on the max accuracy problem. The red line shows the performance of all CPU methods, where all the layers are run on CPU. Although it can achieve the highest accuracy, but it takes a lot of time to run the DNN model on CPU. Therefore, it cannot satisfy the time requirements in many test cases. The blue line represent all NPU methods, where all the layers are run on the NPU. As we can see, its performance does not change as the time requirements changes. Our algorithm max accuracy is shown in the green line, and the MLMP is shown in the yellow line. As we can see from the figure, they have the similar performance for the VocalNet. MLMP slightly outperform max accuracy algorithm. This is because VocalNet is very simple. It just consists of several layers, and both algorithms can find good layer combinations to improve the accuracy. However, for the YOLO model, it consists of dozens of layers, and it is more complex than the VocalNet. As we can see from the figure, when the time requirements is between 300 milliseconds to 750 milliseconds, MLMP outperforms max accuracy. The following figure shows the layer processing time reduction and accuracy loss in the VocalNet model and YOLO model. As we can see, YOLO model consists more layers, and its variation is larger than the VocalNet. Therefore, performing model partition on YOLO model is more difficult. And now let's take a look at the performance of different algorithms on the mean time problem. As we can see, the all CPU method shown in the red line, it can satisfy the accuracy requirements. However, it also has the largest processing time. The all NPU method shown in the blue line, although it has the shortest processing time, however, it cannot satisfy the constraint when the accuracy requirement is above 50% in the VocalNet and 20% in the YOLO model. For the VocalNet, we can see that our MLMP algorithm outperforms the mean time algorithm. And we can observe the similar trends in the YOLO model as well. Now let's draw a conclusion to our presentation today. We studied two different problems in model partition, max accuracy and mean time, and proposed heuristic-based solution to them. And we further improved the performance and address the limitation of the heuristic-based solution by proposing the machine learning-based model partition algorithm. We implement these model partition algorithms and show their effectiveness through extensive experiments. And that's it. Thank you.